A couple more tests for us today because the 5 we have aren't enough yet. So we're going to work on the limit comparison test and the direct comparison test. The limit comparison test is kind of neat, and it's pretty easy to apply. All you have to do is know what's happening with one series, and then if you take the limit of the ratio of the general terms and you get some constant, and that constant has to be greater than 0. So as long as it's some constant, then both of the series either converge or they both diverge. That is, if you know one and this limit is constant, then they either both converge or both diverge. So it's going to rely on you knowing what happens with your one series. Generally speaking, you're going to use something that's pretty easy to work with, like a P series or a geometric series that you just know the convergence outright. The other one is the direct comparison test. This one takes a little bit more finesse to use. So basically, what's going to happen is you have two series, and we're going to assume that all these series have positive terms, and that one of them is consistently bigger than the other one. That is, B sub n terms are always bigger than A sub n terms. Then, if that's the case, then the fact that B sub n, if this series converges, then this one does too. Let's take a closer look at that. I want to spend a little time on this. Now, I wrote this out ahead of time. I'll put it in the notes. So if you're struggling to keep up, don't worry about it. I'm not really going slow for you to keep up. But we want to take a look at a couple different cases here. So this is the comparison that we're going to make. We're going to compare B sub n to A sub n. I'm assuming that A sub n is the smaller of the series. That is, the terms in here are always less than the terms here. Now let's take a look at a couple possibilities. The first one is that this sum is something finite. Let's call it k for some kind of a constant. If this term is a constant and this one is less than that, can this sum up to anything other than some constant, something finite? This also has to sum up to a constant. So if this one converges and this one is bigger than something else, then this one has to converge as well. That would be your conclusion on something like that. Let's flip things around. Let's suppose that the sum of this one is infinite, and these terms are smaller than this one. Well, if this sums up to something infinite, and these terms are bigger than these terms, what's your conclusion have to be about B sub n if the sum of A sub n is infinite, B sub n is even bigger? Also infinite. Nice. So those are the two helpful cases in your terms of your direct comparison test. Now, I tend to favor the limit comparison test because there's a little less thinking involved. As long as you can come up with a series that kind of looks like your other one, you might be in good shape. Let's take a look at this again. We're going to look at the sum of B sub n is greater than the sum of A sub n. If B sub n is infinite, does that tell me anything about the convergence of A sub n? Not really. I mean, A sub n could converge to something finite, or it could converge to something infinite. Or I should say just diverges. So we just don't know. So this case isn't very helpful. Now, the other one that's not very helpful is this one. What if A sub n converges to something finite? We'll call that a k again. Does that tell me anything about what happens with B sub n? No. Just don't know. So, like I said, the direct comparison test is a little bit more nuanced. You have to be a little bit more careful in using this. You know, on the test, on an exam, if you had a choice, and pretty much you will, I'd probably stick with the limit comparison test because there's a little bit less thinking, a little bit less room for error on that one. But, you know, the direct comparison test is something that works. We will use it from time to time. Let's start out with a couple examples, A and B here. And let's see, let me put this as page 3 here. Example A. So we've got the sum from n equals 1 to infinity of 3 over 7n squared plus 5n plus 6. Now let me take a look at this term a little bit more carefully. And this term, we'll call it our a sub n. Those terms. I want to take a look at something that might be kind of similar to that. And that would be 3 over 7n squared. We'll call that b sub n. How are these terms going to compare to each other? Which one's going to be bigger? Well, the numerator's the same, so we don't have to worry about the numerators. Let's think about the denominators. Which denominator has to be bigger? Well, this is going to be a smaller denominator, so this is going to be a smaller quotient, right? If you divide by a bigger number, then you're going to get a smaller ratio. So b sub n is greater than a sub n. Now, what's the good news about that? Let's think about a series of terms with b sub n. If I was to look at the sum from n equals 1 to infinity of 3 over 7n squared, can you tell me anything about the convergence or divergence of that one? The terms will approach 0, so that's kind of like applying our nth term test, but the nth term test can only show divergence. It can't show convergence. So that the terms approach 0 is nice, but it doesn't prove convergence. We actually went over one just like this the other day. I guess what might help you is if I factor out the things that don't depend on n. So a 3 and a 7. N equals 1 to infinity of 1 over n squared. We actually talked about the exact sum of this. It's not something I expect you to know, but you should be able to tell me if this converges or diverges. Why? What is this series effectively right here? Yeah, it's a p series with p greater than 1. So it's going to converge. And since b sub n is greater than a sub n, by the direct comparison test, this series also has to converge. Because its terms in general are smaller than these terms, and this one converges. By the way, does anyone remember what the sum of that series was? I mentioned it the other day. It was Euler that first proved that gem. It was the pi squared over 6. So, kind of cool that somebody could actually find that sum. In any case, you're not required to know that, but you are required to use our comparison test, be it the direct comparison test or the limit comparison test. All right, let's try another one. Are we okay with this one? We're just basically using this idea that if one of them sums up to a finite, if this one sums up to something finite, and it's bigger than another one, this second one has to sum up to something finite as well. Let's take a look at part B then. Example B. Sum from k equals 1 to infinity of ln of 4k over 4k. What's your gut telling you about this one? Do you think it's going to sum up to something finite, or is it going to diverge? What's your gut saying? I suppose I could take out the 4 if I wanted to. 1/4 the sum from k equals 1 to infinity ln of 4k over k. Is there a series that's not too different than this that I can compare this to? Let's just take a look at the denominator. Denominator's, got k to the first power. So the series I'm thinking of would be this one. Compare to sum from k equals 1 to infinity of 1 over k. What's the name of that series, by the way? Harmonic series. Somebody tell me why this diverges. How can you tell it diverges? What's one way to prove it? Very simple way. Nothing? Let me do this here for you. Does that help? Not a p-series with p equal to 1? Yeah, it's exactly what it is. So this is a p-series with p equal 1. What do you know about a p-series with p equal 1? Oh, man. We take a 5-minute break and get some coffee here. All right. What we got? You mean? P-series, p equal 1. Does that mean it converges or diverges? This one, this whole thing. Is that going to converge or diverge? Yeah, it diverges. Now, if I have a series that diverges, that's okay. I can use that one. If this is smaller than something else and this diverges, then this has to diverge. So let's compare these two terms. Let's compare this one to this one. So we'll call these my b sub n, or I can call it b sub k, I guess, because I'm using the k here. I call that a sub k. Which term is bigger? A sub k or b sub k? B sub k. I mean, it's the same denominator, you just got a bigger numerator. So the overall ratio or quotient here has to be bigger than the a sub k's. So we're in this case, we've got a smaller series that sums up to infinity. That would mean that the bigger series has to sum up, smaller series sums up to infinity. That's going to mean the bigger series has to sum up to infinity. So since b sub k is greater than a sub k, and my a sub k diverges, then this series, sum from k equals 1 to infinity of the ln of 4k over 4k also diverges. By the direct comparison test. Nice. Nice. So, another possibility in terms of showing convergence or divergence. I want to keep on going with these possibilities through section 11.5 and 11.6. But how are we looking with that one there? Got a couple nods. Gina is still looking at that one kind of critically.
I just need to do like 5 minutes.
Yeah, these are tough. I mean, like I said, the problem with using this is you pretty much got to know what to expect. So this is why we were practicing some of that stuff the other day, is to just be able to eyeball these things and know roughly what to expect. This is what I do with my series all the time. I look at the terms that are really going to matter. After you start looking at terms like millions or billions, this stuff doesn't really contribute much. Because when you're squaring, let's just use a simple number like 1,000. You square 1,000, you're going to get 1 million. So this term would be 7 million, this would be 5,000. This is going to get kind of lost in the noise from over here. So you're not really going to see that term. Overall, it's going to look like this term. Now, what might be nicer would be to use the limit comparison test here. It's a little less thinking. You don't have to worry so much about, is this bigger, is it smaller, you know. So let's just repeat this one with the limit comparison test, just to see how those things look relative to each other. So let's redo example A with the limit comparison test. So example A with the limit comparison test. All right, so let's see, we've got this series again, sum from n equals 1 to infinity of 3 over 7n squared plus 5n plus 6. And because most of this term is going to be dominated by just this little bit, let's compare that. Compare to this series, the sum from n equals 1 to infinity of 3 over 7n squared. Are you understanding why I chose that term to compare it to? It's because overall, this part of this series doesn't matter. And there's also a bonus. We know that this thing converges. You can get rid of the 7 and the 3 and just look at the part that remains, 1 over n squared. You know that's a convergent p-series. So we know this one converges. So if we can apply the limit comparison test and get a finite number, then we'll know this one converges as well. You don't have to worry about what's bigger, what's smaller. You're just going to do a little calculation of a limit. So let's call these our terms and call that our b sub n. That's our a sub n. We need to form the limit as n approaches infinity of a sub n over b sub n, which would be the limit as n approaches infinity of 3 over 7n squared plus 5n plus 6 divided by 3 over 7n squared. And that's a really awful looking 7 there. Let me see if I can't clean that up a little bit. That's a little bit better. What's our trick in terms of working with fractions? When you divide by a fraction, you multiply by the reciprocal. So this is the same as the limit as n approaches infinity of 3 over 7n squared plus 5n plus 6 times 7n squared over 3. Okay, so I see a lot of nice cancellation here. Well, maybe not a lot, some. The 3's cancel each other out. Try and impress me that I don't really need to bust out L'Hopital's rule here. What's that limit going to end up being?
1.
Yeah. If you said 7 over 7, I'm sympathetic to that. That's 7 over 7. That's fine. But then it reduces to 1. Now the important thing is that this limit is between 0 and infinity. It can't be 0. It can't be infinity. As long as it's some finite number other than 0, then you get convergence of this series because of convergence of this series. So therefore, the series this one, n equals 1 to infinity converges by the limit comparison test with this series, n equals 1 to infinity of 3 over 7n squared. Nice. Any preference? Was the limit comparison test a little easier to work with, or well, you got them both, all right? It's not going to be very often that I'll tell you you have to do it this way or that way in terms of these tests. I'm pretty flexible about that. Andreas?
How do you know which one to call A sub n or B sub n?
That's a great question. It wouldn't matter. The limit would still be the same either way.
Okay.
Yeah, so it's a good question. It's not going to matter. Yeah. So, in case you didn't hear, her question was like, well, how do you know which one to call A sub n and which one we call B sub n? If I had these flipped, I'd still get the same limit, you know, and it would still be a finite limit. So suppose I use just 1 over n squared. For whatever reason, I'm in the habit of using like the 3 and the 7. So a lot of times these limits for me will turn out to be a 1. But you don't have to. You could have just as easily used 1 over n squared. If we'd used a 1 over n squared, then I'd still have a 3 up here. That'd be fine. But I'd end up with a limit of 21 over 7, which would be 3. So again, it would be finite, and I'd still be proving the convergence with a limit comparison test. So yeah, appreciate the question. Thank you. Anything else on this one? Okay. Let's do a bunch more. Let's try and guess first about whether or not you think the series is going to converge or diverge before we actually jump into it. When I look at example C here, so let's see, 5, example C. I look past the finite number of 6, sum from n equal 1 to infinity of n plus 6 over n times the square root of n. Okay. I'm going to rewrite the denominator. Still have the n plus 6 here in the numerator. But let's think about what's going on in the denominator. Square root of n could be rewritten as n to what power? 1/2. 1 plus 1/2 is going to give me a total of n to the 3/2 power here. Now when I look at this, I'm thinking that 6 isn't really going to matter. So I'll replace this with an approximately equal to n equal 1 to infinity of n over n to the 3/2. This is just kind of rough and ready work here. I am throwing out that 6 term, but it kind of gives me an idea of what's going to be important overall. Because when you get up to terms like, you know, in the billions and trillions, etc., that plus 6 is not going to make a big difference. But what can you say or think about this series? What do you think there?
Probably going to diverge.
Probably going to diverge? All right. Sounds like a reasonable bet, but why?
If you divide the ends into each other, you'll get
Yeah, there you go.
number, and square root of n to the 1/2, and P series is going to say that's going to diverge.
Exactly. So the thing to notice here is that I could simplify this a little bit further. Because I got n to the first power and n to the 3/2 power, and opposite sides of a fraction, I could subtract the smaller from the larger. This is going to be the sum from n equals 1 to infinity of 1 over n to the 1/2 power, which this much is a divergent p-series. Diverges, that's a p-series. Diverges. P-series, p equal to 1/2. P equal 1/2. Okay, so we kind of expect it to diverge. And in fact, this isn't a bad term to work with as far as using something to compare to. Now, you could probably spend a lot of time and try and figure out if you could use a direct comparison test in some way or another. But for my money, I've already got something that I know what's going to happen with this series. This one diverges. Let's just use that for part of our limit comparison test. So, Andreas, tell you what, I'll give you the honor of deciding what's going to be my A sub n and what's going to be my B sub n in this particular case. So, choice is up to you. Doesn't matter, just throw out this is A sub n, this is B sub n, or vice versa.
Yeah, let's do that.
All right.
Then we can fill in the rest.
All right, perfect. A sub n and B sub n. So let's take a look at the limit as n approaches infinity of n plus 6 over, I'm just going to write n to the 3 halves here. It's going to be easier than dealing with that n times the square root of n over 1 divided by n to the 1/2. We'll play our same game that we did before, and that is invert and multiply. So that's going to equal limit as n approaches infinity of n plus 6 over n to the 3 halves times n to the 1/2 over 1. Anything you can see that might help us work on this limit? Got any ideas here? Yeah. Since you've got, everything is being multiplied together and these are on opposite sides, we can cancel out half of those, right? What's that going to leave me in the denominator? Yeah, n. So I'm left with n plus 6 over n. Cameron, what's that limit going to be, please?
That's going to be infinity over infinity, but then if you use L'Hopital's rule, it's just 1.
Yeah. So we can use L'Hopital's rule and get that. Is there somewhere else we can get that limit to? There's nothing wrong with Cameron using the L'Hopital's rule. Well, what else can I do to get that limit? Yeah, our power rule. Both of these have the same exponent. They're both polynomial terms. So it's just going to be a ratio of those leading coefficients, 1 over 1. Looking good there. And that's 1. Nice. All right. Yeah. Limit comparison test works pretty nice, especially once you get a handle on what you want to compare it to. And I hope that you kind of followed along my logic up here, that some of these finite numbers really aren't going to make a big difference. So you start looking past that. And then we simplify that and realize, oh, this is not too far away from a term that we know diverges. And we just use the limit comparison test from there. Okay, let's keep rolling. Example D. I want you to figure out what term we're going to compare it to and if that series is going to converge or diverge. So we got the sum from n equal 1 to infinity of 9 to the n over 8 plus 11 to the n. If you're watching this later, give yourself a moment, but try and figure out a good series we can compare that to. Are you going to use the direct comparison test or the limit comparison test? What are you going to do?
What's the conclusion to example C? Like they both
Oh.
converge or they both converge?
Yeah, sorry about that. So go back here real quick. Because this is finite and greater than 1, or greater than 0, therefore both series converge. All right, both series diverge.
And that's because the other one diverged and they have to match.
Yeah. So what happens with one series is going to happen with the other series. So we know that this one diverged, and because when we did that limit comparison ratio, we found out that we got a finite ratio. That means this one also has to diverge. So they behave alike.
Thank you.
Yeah, no, I appreciate the question. All right, go back there. So he's like, yeah, but I appreciate the effort.
Yeah, that's
Okay, what kind of series is that? That's your Do you scan these? Scan them. Scan those in and then write on the scans. Yeah, no, that's pretty cool. Okay. Is that one converted? Okay, so what does this look like that I might be able to compare it to? What series would you start with? Like, well, okay, it kind of looks like what? I need to hear from you guys. I know what it is, but Gina?
I went with 9/11 in parentheses to the end.
Nice. So let's call this n equal 1 to infinity. And I'm going to do it in a couple steps in case you need that. You get 9 over n over 11 over n. We're just kind of ignoring that a little bit. But if you heard Gina, she actually rewrote it differently. She wrote 9 over 11 raised to the n power. And that's where you want to get with this one. Why? What's going on with that series that we actually know? What do you know about this series? What kind of series is it? Got nothing on that one? Come on, somebody. Say again?
Geometric series.
Geometric, yeah. Geometric. Sorry. Does it converge or diverge? Good. Converges why? Yeah. Converges because 9 over 11 is less than 1. Okay, so we've got a nice convergent series that we can compare it to. So we think that they both probably converge. Now, trying to think which one I want to use. You could use a direct comparison test in this case, or you could use the limit comparison test. I'm wondering if the limit comparison test would be kind of a mess because we don't have polynomial terms, we have these exponential terms. So let's see if we can't use the direct comparison test in this case. how is this term going to compare to this term? Is it going to be bigger? This one's going to be smaller, right? It's got a larger denominator, the same numerator, so this one has to be smaller. Now, that's okay if you're trying to use the direct comparison test and show that you have convergence. So we've got something that's finite, which is bigger than something else, so we should be able to show that this one's finite, therefore this one has to be finite. That's where we're going with this one. Actually, there's not much more to do on that, I don't think. So we can call this one our A sub n, and those will be our B sub n. Actually, no, I'll just do it here. B sub n. Because B sub n is greater than A sub n, then this summation, n equals 1 to infinity of 9 to the n over 11 to the n, has to be greater than this summation, 9 to the n over 8 plus 11 to the n. Then, because this one is finite, this one has to be finite. And the series must converge because of the limit comparison test. Or excuse me, the direct comparison test. The hard part in these is coming up with a series that you're going to converge or compare to. That is something I'll ask you on an exam. If you're going to say it converges or diverges by the direct comparison test or the limit comparison test, I want to know what series that you're using as you do these problems. But a lot of the work that I do in my head is what I'm trying to verbalize for you now, and that is, well, let's look at the important parts of the series. That 8 is not going to be a big thing after a while. So we looked at this, turns into a geometric series. We get a nice quick approximation. You could also do that with a limit comparison test. I'm just thinking that the limit comparison test in that one would be a big mess because of the exponents there. Let's do a couple more, and then I want to turn it over to you to work on some of these things. So example E. Got the sum from n equals 1 to infinity of n plus 7 over n plus 5 to, what is that, the fifth power? Fourth power? Thank you.
It says n equals 12 as well.
N equals 12? Okay. It doesn't really matter that it starts out at 12. It could start out at any number you want, as long as it's going to infinity. That bothered me when my calc instructors were telling me, like, yeah, well, you could throw out any finite number of terms. You know, what happens, what's important is what happens towards the end of this. As you get out a long ways, what's happening when you get near infinity. And he's right, or he was right. You know, what happens with the first few terms is just going to be finite no matter what. What's really going to count is what's going to happen at the end. Now, question for you. What do you think is going to happen with this one? Are we going to end up being, we're going to end up with something that converges or diverges? What are you thinking on this one?
Converges because the denominator is larger.
Okay, converges because the denominator is larger. In fact, let's take a look at the denominator. The denominator has something to the fourth power, right? The numerator only has something to the first power. So if I was going to kind of approximate this stuff, I would look at sum from n equals 12 to infinity of n over what? Let's just go n to the fourth. All right, let's just kind of bypass those finite terms. Then what? Yeah, somebody said the magic word. This is 1 over n cubed. Somebody back there, who was it? All right, thank you, Marlon. What's this got going for it? P series with p equal 3. So if the p series of p equal 3, Brandon, is that going to converge or diverge?
That is going to diverge.
Diverge?
The other one.
All right. I was going to go to Brandon for a second opinion and then Brandon for a third opinion. All right. So this one converges. Converges. So let's take a look at, I would do the limit comparison test personally. We'll call that my A sub n. This is my B sub n. Let's take a look at the limit as n approaches infinity of A sub n over B sub n. Which is going to be the limit as n approaches infinity of n plus 7 over n plus 5 to the fourth power over 1 over n cubed. Let me bring that down here. Equals limit as n approaches infinity of n plus 7 over n plus 5 to the fourth power times n cubed over 1. N approaches infinity, n to the fourth plus 7n cubed over n plus 5 to the fourth. This one might not be as clear to you what this limit is, but maybe it is. I don't know. What would that be if we took the limit?
1.
Yeah, it's going to be 1. Oh, I'm impressed. I'm glad to see it. We've got an n to the fourth here, and if the fourth power version of FOIL this out, if you use Pascal's triangle, for instance, you're going to end up with n to the fourth plus something. And it doesn't matter what the somethings are after that point. We know that you're going to have a coefficient of 1 for your n to the fourth term. So we'll end up with a 1 in the numerator and a 1 in the numerator and 1 in the denominator. So you get a limit of 1. And that's what we're looking for. We're looking for a finite limit. Now, it doesn't always have to be 1. It's just the quirk of the way I do these things that I often end up with a 1. It could be 7, it could be 700, it could be 7 million, as long as it's finite and greater than 0. So, by the limit comparison test, our original series converges. So, therefore, by the limit comparison test with 1 over n cubed, the series n equals 12 to infinity converges. That'd be a 5. The fourth power converges. Yay. How are these looking? Looking okay? Syed? That was a genuine thumbs up over there. All right, that's cool. If there's something about this that you're like, how'd you do this or something like that, please reach out. Will, doing okay on these? Is there some detail I can add someplace? Maybe one of my steps I skipped too much? No? All right, yeah. Certainly practice is key. We're going to take some time to do some practice today. Let's see. Yeah, we'll make this our last one. Then I'll break up into groups and we'll do the 2-minute drill again. So example G. The sum from n equals 1 to infinity of, a little too dark over here, n over 4n cubed plus 5.
Do you mean example F?
Is it F?
Yeah.
Yeah, my bad. Thank you. Example F. Think about this one. Decide for yourself if you think it converges or diverges first. And then proceed with either the direct comparison test or the limit comparison test, whatever works for you. Talk to your neighbor. Do you think it converges or diverges? You guys in agreement on that?
I don't understand that one as well, so I just do it. Yeah, I think generally it's like
That's your comparing to the and that's just P series.
All right, so I think we're doing good on this. I think a lot of you are seeing the logic that I follow through when I do this, and you're looking at that going, well, that's about n equal 1 to infinity of n over 4n cubed, which equals sum from, I'll take out the 1/4 here, n equals 1 to infinity of 1 over n squared. And what do you know about this one? Convergent p-series, right? P equal 2. So you're thinking that, well, that one looks like it probably converges because this one converges. So we can use the limit comparison test there. You know, let's see, can you use the direct comparison test? Yeah, you could. Sure, you could. I don't know. For myself, if I can use a limit comparison test, I'm happier. So we'll do that. A sub n. And I'll call this our b sub n, but I'm going to simplify it to 1 over 4n squared. So the limit as n approaches infinity of, let's see, n over 4n cubed plus 5 divided by n over 4n cubed. invert and multiply, limit as n approaches infinity of n over 4n cubed plus 5 times 4n cubed over n. Well, we get some cancellation here. You're going to end up with limit as n approaches infinity of 4n cubed over 4n cubed plus 5. That limit is 4 over 4, which is 1. Nice. Lionel, something? Gina?
Pretty much I think every time you've done this problem at the end, you said the series must converge because of whatever test you did. Are you expecting us to do that on the exam, say what we used?
Unless it's clear to me in some other way, yeah, I'd like to. It's just okay to use a full sentence on a math test. Yeah, it's legal in most states and a few Canadian provinces as well too. Yeah. All right. So therefore, this series, and I'll say write this sum from n equals 1 to infinity of n over 4n cubed plus 5 converges by the limit comparison test, which I'll abbreviate with, was it n over 4n cubed? So we'll just do it like that. Yeah, I'm sympathetic to it's like, all right, we've done all this work and now you're gonna make us write a sentence. So appreciate it. Okay, how's that one looking? Starting to go okay? I think you notice by the way we worked our way through the problems here that I'm not a huge fan of the direct comparison test. I can't tell you how many times I've been grading things and I see people doing the direct comparison test the wrong way. That is, they have something infinite here, doesn't show the convergence of something here. And something finite here doesn't show the divergence or convergence of something here. It's why I tend to favor the direct comparison test, because once you know what to expect, direct comparison test is just a nice calculation. So, any last thoughts on this section? Nice. All right, let's put this one to rest.